To begin, action potential moves into the axon terminal. Voltage-regulated calcium channels are opened. Calcium flows through the channels into the axon terminal. It binds to the vesicles, which contain acetylcholine. The vesicles travel to the axon terminal membrane and performs exocytosis, releasing the acetylcholine into the synapse. The acetylcholine attaches to the ligand-gated sodium channel. The channel then opens and sodium travels from the interstitial fluid of the synapse into the muscle fiber. The charges of the synapse and the muscle fiber switch. The muscle fiber is now positive and the synapse now has a negative charge. The sodium that was passed through the ligand-gated sodium channel travels down the membrane, along with action potential. The acetylcholine is returned to the axon terminal by acetylcholinesterase.
The action potential causes the voltage-regulated sodium channel to open. Sodium from outside the membrane travels into the muscle fiber. Due to the imbalance, the charge inside the muscle fiber changes from negative to positive, and the charge outside of the membrane changes from positive to negative. This change in charge is known as depolarization. As action potential moves, the sodium channel shuts and the voltage-regulated potassium channel opens, allowing potassium to flow from the muscle fiber to the outside of the membrane. Sodium-potassium pump is operating the entire time, powered by ATP. The combination of the pump and the potassium channel cause repolarization as the charge is reset back to normal. Potassium channel closes and the pump continues to work, causing hyperpolarization of the muscle fiber. This hyperpolarization prevents the process from moving backwards. As action potential moves forward, the process repeats itself.
As the action potential moves down the T-tubule, it hits a switch on the sarcoplasmic reticulum. This switch triggers the voltage-regulated calcium channel to open. The calcium from inside the sarcoplasmic reticulum travels out to the sarcomere and lands on troponin. It activates the troponin and the tropomyosin peels back, revealing the myosin receptors. The myosin heads attach to the receptors, reducing the Bayer zone and causing the muscle fibers to contract. ATP binds to myosin in order to release it from the myosin receptor and recock it. Myosin is now highly energized, and as the ADP releases from it, the myosin head flings forward, attaching to another receptor. As the calcium releases from the troponin, it is pumped back into the sarcoplasmic reticulum by a calcium pump, which is powered by ATP. And that's muscle contraction.